So let's apply the binomial theorem now. So previously we had seen the binomial theorem. It looks like this. So it was a plus b to the power of n is equal to the sum from k is equal to 0 to n of n choose k times a to the power of n minus k times b to the power of k. And this is true for all non-negative integers n and real numbers a and b. So from this we were able to get all sorts of different forms varying n. And I want to show you how you can apply this binomial theorem in a few different ways. So here's a few different ways of applying the binomial theorem. So the first one is I'm going to try applying it directly. So I'm just going to verify something that I told you to think about. Is you can just pick it for a particular value of n, and it'll give you the form that you're desiring. So, for example, if you picked n is equal to 2, you'll end up with the result of what maybe your teachers taught you how to do FOIL. And then you end up with the result of that. That form falls out of this theorem at n is equal to 2. So let's apply this directly. So I must stress that that's when a and b are equal, just to be clear. But anyways, we're going to try to see what happens with the binomial theorem if we fix n and then see what form we get by multiplying a plus b 3 times. So I have sorry, I'm getting really excited here. I need to calm down. I'm just so dang excited. So what I want to do is I'm going to fix n, and I'm going to simplify so that I can get a form that I can use to evaluate some polynomial, for example. Let's consider n is equal to 3. So this is something actually I asked you to do in a previous lesson. So let's try with n is equal to 3. So rather than having to compute n is equal to 2 and having to do all that work, I can use the binomial theorem directly. So k is equal to 0 up to 3 of 3 choose k of a to the power of 3 minus k, b to the k. So let's see what we get here. So I'm just going to write out for each value of k. So we start at 0. So we have 3 choose 0 times a to the 3. So a cubed, b to the 0 plus 3 choose 1 times a squared b to the power of 1 plus 3 choose 2 a to the power of 1 b squared plus 3 choose 3 of a to the power of 0 b to the power of 3, or b cubed. Notice I could simplify this further, but as I want to stress again, this is just a row in Pascal's triangle. So please just keep that in the back of your mind, these coefficients here. So I have 1 times a cubed times 1, right? B to the 0 is just 1, plus 3 times a squared times b plus 3 choose 2 is the same as 3 choose 1. So it's just 3 times a b squared plus, so a times b squared. And then 3 choose 3 is just 1. 1 times a to the 0 is just 1 times b cubed. So let's simplify this now. We have a cubed plus 3a squared b plus 3ab squared plus b cubed. So if you ever needed to multiply a binomial by the exponent 3, it would have this form. If you try it with 2, you'll notice you'll get a very familiar form if you're familiar with the FOIL method. So let's see another way we can apply the binomial theorem. So we can figure out a and b carefully and then use the binomial theorem. So I'm just going to colloquially refer to this as figuring out out A and B. So these are just a few ways to use binomial theorem. By no means is this the only thing. So we'll see another example of how we could use the binomial theorem. But let's consider this example. So suppose we wanted to derive a closed form. Wanted a closed form expression or formula. A closed form expression for the following. So suppose I want to have this for the sum from I is equal to 0 to n of n choose I times 7 to the power of I. So it's slightly different. I changed the variable from k to I just to make it clear that it doesn't have to be k or anything like that. It's just a name. So the sum from I is equal to 0 to n of n choose I times 7 to the power of I. Now, I want you to go back to over here. Notice that if I were to pick A and B carefully, I might be able to match the form I have over there. Do you notice that I have 7 to the I over there? That's like B to the K over here. If I were to somehow get rid of the A, then I can get something that looks like that over there, right? But what would I pick as A then? What's something that if I raise it to any exponent is always 1? Well, 1. One's a good place to start. Notice on the right-hand side, of the binomial theorem, when A is equal to 1, then we have this property that A to the power of n minus k is equal to 1. So applying the binomial theorem, with A is equal to 1 and B is equal to 7, right? Because that's what the other term would be, right? That's what B to the k, this would be a 7 here. So if I want it to look like that, well, it tells you everything, right? Well, what does it say? The sum from I is equal to 0 to n of n choose I of 7 to the power of I is equal to the sum from I is equal to 0 to n of n choose I of 1 to the n minus k. So I'm just going to shove a 1 in here to make it look like the A over there times, sorry, not n minus k, we need n minus I. So same thing here. N minus I times 7 to the power of I. Miss Kitty, where are you? Okay. Anyways, the binomial theorem says that this is in fact equal to 1 plus 7 to the power of n, which if you simplify, this is just a to the power of n. So if you need a closed form for this. Well, I know she was sort of having a great battle with Mauchi just a little while ago over there. It was pretty epic. But yeah, no. So that's a to the power of n right there. So that's a second example. Let me show you a third one. This is more for those that are the algebra enthusiasts. Is that if ever you have something that looks kind of like the binomial theorem, we can kind of substitute parts of your expression into it if it has the conditions of the binomial theorem. So let's try a third example. So the third example here I'll just refer to colloquially as fitting the form. So fitting the form. So I'm going to give you something that does not look like the form of the binomial theorem. And then I'm going to show you that you could just actually fit it carefully in, and then you simplify. So watch this. So consider the expression for variables x and y, 2x minus 3y squared, like this. Now, at first, this doesn't look like anything resembling the left-hand side of the binomial theorem, right? It doesn't really look like it, but it actually is hiding that form in here. So rewrite, because remember, the theorem says that as long as it takes the form of a plus b to the power of n, where a and b are real numbers, we're okay. So we're going to rewrite that guy like this. So I can take anything that's like a difference like that, and I can replace it with addition where I negate. Like this. So I have 2x plus minus 3y. So it's the same thing, right? Squared. Right? You would agree with me that taking away is the same as adding what you're going to take away. Right? So I'm just simply saying, hey, look, instead of just saying take it away, I'm going to make it so that you have to add what you're going to take away. Meaning that you're going to anyway take it away. But I'm just doing it over this so it looks more like the form, right? So now I have something that looks like an A and something that might look like a B. So what I'm going to do is I'm going to let 2x be A, and I'm going to let minus 3y be B. Because this will work because A and B, as long as they're real numbers, we can use the binomial theorem. So applying the binomial theorem, and we're going to use it when n is equal to 2, right? Because the exponent was 2. With n is equal to 2 and a is equal to 2x, b is equal to minus 3y, we end up with this. Minus 2x plus minus 3y squared is equal to the sum from k is equal to 0 to 2 of 2 choose k times 2x raised to the 2 minus k multiplied by minus 3y to the power of k, right? If you're not convinced that that is the form, just put a and b in and see if it matches up with what you'd expect. Okay. Now, next what I'm going to do is I'm going to expand this out term by term, varying on k. So I have 2 choose 0 times 2x to the power of 2 minus 0 times minus 3y to the power of 0 plus 2 choose 1 times 2x all together, right? 2 minus 1 times minus 3y to the power of 1 plus 2 choose 2 times 2x to the power, so this, remember, it's all together, 2 minus 2 times minus 3y to the power of 2. So 2 choose 0, that's just 1, right? So this is just end up being, okay, and also minus 3y to the power of 0, that's also 1, right? So this is 1, 1, so you end up with just 2x all together squared, right? Now, 2 choose 1 is just 2, right? Then this is just 2x itself, right? Because it's raised to the power of 1. And then I have minus 3y raised to the power of 1. So I have 2 times 2x times minus 3y plus this one, 1 times 2 minus 2, that's 0, right? So this is just going to end up being a 1. And then we just have minus 3y squared like that. Minus 3y squared. Now, got to remember, if we square something that's negative, what it happens to it? It becomes positive. Well, I'm going to carry in the square here, so I'm going to square this, square that. So I have 4x squared plus, now we have 2 times, so we got 2 times 2, that's 4, times minus 3y. So I have 4 times minus 3 is minus 12, right? But it's multiplied by x and y, so it's minus 12xy. And now remember, minus 3y. So remember, this is y squared times minus 3 squared, which is 9, not minus 9. So it's plus 9y squared. So now we've received a form based on this. So this is how you could expand using the binomial theorem. So sometimes you might want to try fitting the form into the binomial theorem.